Hello everyone. Today we will discuss about that every linear transformation on a complex field has an eigenvalue. Means what if we have a linear transformation T and it is from C over C. Okay, sorry. So we have a linear transformation from vector space C to vector space over C. Then we have a eigenvalue, at least one eigenvalue from the field C. Okay, so we will show this by showing that if we have a vector v which is non-zero, then we can make vector v t of v t square v dot t and v are linearly dependent. Okay, we try to construct n plus 1 linearly, n plus 1 vectors, or since vector space is n dimensional, we have assumed finite dimensional. Let's assume it is n dimensional. So n plus 1 vectors will be always linearly dependent, and these vectors are linearly dependent. Okay, so we have there exists a naught a1 e2 dot an belong to complex field, not all zeros, because these are linearly dependent. So at least one of the constant will be not equal to 0, such that their linear combination equal to 0. Okay, so linear combination means what? A naught v plus a1 t of v plus a2 t of t square v dot an to the power n v equal to 0. Okay, here v t of v, these are vectors. Okay, t to the power n means we have operated t n times. Okay, also if a1 a2 dot an is 0, let's assume a1 a2 dot an is 0, this will implies a1 v equal to 0, and if a naught v equal to 0 and a naught v, in a naught v, if v is non-zero, we have assumed v is non-zero, then a naught will be 0. So all the constant a naught a1 dot an, these will be zeros. So a1 a2 an, in which at least one will be non-zero. Now p is non-zero, so a not equal to 0, and this becomes linearly independent. Okay, so now we try to make a polynomial by the help of these constant a naught a1 a2 an, and polynomial will be in t variable. Okay, so here a naught v plus a1 t of v plus a2 t square v dot an to the power nv. We have made this polynomial and it will be factorized. Okay, so since field is complex, it can be factorized. Okay, so it will be factorized t minus lambda 1 I, c will be constant here, multiply by t minus lambda 2 I dot t minus lambda m I v equal to 0. Here actually v is outside because it is a linear transformation, and sum of two linear transformation is again a linear transformation. In linear transformation we can out a vector. Okay, so that's why we have firstly v has been out and then we have factorized. Okay, now these factors is equal to 0 because here this term is equal to 0 and we have factorized this term only. So at least one of the factor will be 0, and assuming t minus lambda 1 I equal to 0, assume this term equal to 0 because it can be commutative. Here t minus lambda 1 I is the first term, we can take this term in the last, so it will be t minus lambda 1 I v equal to 0, so it will be T of V equal to lambda 1 V. So we have proved that there is at least one constant. It may be in real, it may be in complex, okay, so such that T of V equal to lambda V, and V is non-zero, that will be an eigenvector.